Today's session is about chord of the ellipse. Now, as we have discussed chord to be the line segment which cuts the circle, as we have seen the chord of the circle is the similar definition which you're going to see for ellipse. So let's define the chord of the ellipse. For example, I take the ellipse x-axis, y-axis and origin. Then the chord of the ellipse is the line joining any 2 points of the ellipse. Say for example, if there's a line which cuts the ellipse in this manner, then clearly this line L cuts the ellipse at A and B. Therefore, AB is called the chord of the ellipse. So a line segment joining 2 points of the ellipse is called the chord. So this is referred as the chord. Is the chord of the ellipse. So we have infinitely many chords which exist in the ellipse. You have a chord passing here, a chord passing here, a chord out here, and here. So there are infinitely many chords which exist inside the ellipse because there are infinitely many points on the ellipse. There exists infinitely many chords for ellipse. Is how we conclude the chord of the ellipse is the line joining any 2 points on the ellipse. The line segment in the ellipse here being AB is the chord, for example. The next is the focal chord. So what is a focal chord? As you have seen that chord is part of the ellipse, the line segment joining any 2 points of the ellipse. That line segment, if it passes through one of the focus or foci, is called focal chord because the word focal itself refers to the line passing or the chord passing through the focus. Now, as we have 2 focus for the ellipse, say as we have 2 foci S and S dash for the ellipse, so a line segment a chord which passes through either S or S dash is called a focal chord. So for example, if I have a line segment which is passing through this, and there's another line segment which is passing through this, say this one, and there's another line segment which is not passing through the focus. Now in these cases I say that AB, which is passing through S, the focus S, is called the focal chord. Now similarly, as I see the line segment PQ which passes through the other focus S dash is also the focal chord. But the line segment LM which doesn't pass through either S or S dash is not a focal chord, but it is just called the chord. So this is how I differentiate between the chord and the focal chord. The focal chord refers to the chord passing through focus, and a chord refers to any line segment which passes through the ellipse. And of course, this can also be called as chord because a focal chord itself has the word chord. So AB, PQ and LM are chords and AB and PQ are focal chords. So this is how we identify the difference between the chord and the focal chord, as can be seen with this example out here. Next, about latus rectum of the ellipse. Now, latus rectum is a focal chord which is perpendicular to major axis of the ellipse. So, for example, I have the ellipse with focus S, with foci S and S dash, then latus rectum is a focal chord which is perpendicular to the major axis. This being the major axis and this being the minor axis, LL dash is a latus rectum because it is a chord passing through focus, that is the focal chord, and which is perpendicular to the major axis. LL dash passes through focus S and LL dash is perpendicular to X dash, which is the major axis. And this is the minor axis, is how we identify. Therefore, LL dash is latus rectum. This is how we define the latus rectum, which is a focal chord which passes through focus and which is perpendicular to major axis. So this is the condition which makes the focal chord to be latus rectum. So there are two focal chords, there are two latus rectums for ellipse. One is LL dash and the other is, you can say, M dash. So there exist two focal latus rectums for the ellipse which are perpendicular. One is LL dash and one is M dash. Is how we understand the latus rectums for the ellipse. And the plural for latus rectum is latera recta. That is, there are two latera recta for the ellipse, or two latera recta for the ellipse, LL dash and M dash. Now let's see the learning outcome of the three topics which are taken, that is the chord, the focal chord and the latus rectum. As we have three things, one is the chord, the next is the focal chord, and thirdly it is latus rectum. We identify that there are infinitely many number that is, for an ellipse there are infinitely many chords which I can draw. As you can clearly see that an ellipse has infinitely many chords which I can draw out here. So each of them is a chord as part of the line cuts the ellipse at two distinct points. Now as I see the focal chord, also there are infinitely many. Because even in this case, if I take the ellipse and I have the focus S and S dash, there are infinitely many lines which I can draw through S, and there are infinitely many lines which I can draw through S dash, as can be clearly seen from here. So chords, there are infinitely many, and focal chords, there are infinitely many. But when it comes to latus rectum, we have already seen that as I see this, there's only one line which is perpendicular and passing through focus, and therefore these two, there are two latera recta, infinitely many focal chords and infinitely many chords, is how we make the learning outcome of each of the chord, focal chord and latus rectum in number. Length of latus rectum. So now that we have discussed about latus rectum, let's see what is its length in its mathematical formula. So let's draw the lattice rectum for the ellipse. This, where I have x-axis, y-axis in this way. Now let me take one of the lattice rectum which passes through the focus S, which are given by coordinates a, 0. So we know that the lattice rectum is a chord passing through the focus and perpendicular to the major axis. So clearly LL dash is the lattice rectum. So with this lattice rectum, let me find the coordinates of A, L. So coordinates of L are given by AE, B square by A and AE, minus B square by A, and this is the length of the lattice rectum. So LL dash is said to be length of lattice rectum. So this length of lattice rectum is given by LL dash equal to 2b square by A units, is how we identify the length of lattice rectum is 2b square by A units, and the endpoints L will be AE B square by A and L dash will be AE minus B square by A, which are called the extremities of the lattice rectum, which are called the extremities of lattice rectum. So L and L dash are the extremities, with L given by A, B square by A and L dash given by A, minus B square by A, and the length of lattice rectum LL dash is 2b square by A units. This distance being 2b square by A units. That's how we identify the length of lattice rectum. Now, since there are two lateral recta, one of the lattice rectum being LL dash, the other lattice rectum would be here with S dash being minus AE, 0. Therefore, if I join this and if this is perpendicular to the major axis, then the lattice rectum MM dash is called the other lattice rectum on the negative side of x-axis. So the length of the other lattice rectum is also 2b square by A units, is what we identify. The length of both the lattice rectums are equal, and this will be equal to this, and each of them are with value 2b square by A units. And the extremities endpoint M is given by minus AE, B square by A, and M dash is given by minus AE minus B square by A, because M and M dash lie on the negative side of x-axis, both will be minus. Is how we identify the other lattice rectum with the length and endpoints. Lengths are same, the endpoints change. So therefore there are four extremities LL dash, MM dash, and two lengths of the lateral recta, this and this, which are equal. Is how we understand the concept of lateral recta connected with the lengths and extremities of through the ellipse. Now let's see the equation of lattice rectum. As we have seen the length, now comes what would be the equation of the lattice rectum. Now since there are two lateral recta, we have two equations which we need to identify in case of this topic. So in this case, I have an ellipse X and Y which is an ellipse. and we have the lattice rectum through A0 and another lattice rectum through minus AE. Is how we get the two lattice rectum. Now in this case, we need to find equation of this lattice rectum and equation of this lattice rectum dash also. Now as I clearly see here, this is a line which is parallel to y-axis and at a distance of AE units from origin. Therefore, this is a line being parallel to y-axis. Equation of lattice rectum is x equals AE. And equation of this lattice rectum is x equals minus AE. So are the two lattice rectums or the two lateral recta which we see, one of the equation is x equal to AE and x equal to minus AE. So equation of LL dash is x equal to AE. And equation of dash is x equals minus AE, as we can see here, this and this. Equations of the two lateral recta LL dash and dash are x equal to AE and x equal to minus AE. Now let's see the equation of lattice rectum if A is less than B. That is, if I have an ellipse x square by a square plus y square by b square equal to 1 with a less than b, then with this condition we have the ellipse in the shape like this. X, y is what we get. Now because A is less than B, we have the ellipse with major axis on y-axis and minor axis on x-axis. Therefore, the focus shifts to y-axis as S and S dash. And the coordinates of S are 0, BE, and this is 0 minus BE. Therefore, the lateral recta passing through focus S would shift in this manner with L and L dash, and this lateral recta would shift with M and M dash is what we get. And therefore, equation of LL dash would be, this is a line which is parallel to x-axis. Therefore, if I draw a line parallel to x-axis and at a distance of BE units from origin, then clearly I have this line to be y equals BE. And this with equation of MM dash, which is a line parallel to x-axis but below origin with the distance being BE, will be on the negative side of y-axis, and hence I have this to be y equals minus BE. So equation of MM dash is y equals minus BE is how we identify the equations of lateral recta LL dash and MM dash in this case. Now next comes the length of lattice rectum for A less than B. So let's take even the length of lattice rectum which we need to identify for this topic. Now let's see the length of lattice rectum for A less than B. Now as I've seen that the lattice rectum, the lateral recta are LL dash and MM dash, the endpoints of the lateral recta are given by L, which is 0 BE, A square by B, comma BE, and L dash given by minus A square by B, comma BE. And for M, it is minus A square by B, comma minus BE, or this is plus A square by B minus BE, and this is minus A square by B and minus BE. Is how we get all the four end extremities of the lateral recta for A less than B. So I have my L given by A square by B and BE, and L dash, which is minus A square by B and BE, which are the extremities of the first lattice rectum L dash. And the other extremities are M, which is A square by B minus BE, because it comes in the negative side of y-axis below origin, and M dash is minus A square by B minus BE. Is how we identify the two sets of extremities LL dash and MM dash. And coming to the length of lattice rectum, my length of lattice rectum, which is given by LL dash, also given by MM dash, because both are equal, is given by the formula 2A square by B. Is how we identify, as can be clearly seen here, that this distance is A square by B and this distance also is A square by B. So A square by B plus A square by B is 2A square by B, which is LL dash, and hence the length of lattice rectum LL dash or MM dash, because these two are equal, is 2A square by B units. Is how we identify the length of lattice rectum for the ellipse with A less than B. Now let's take the standard equation of ellipse with A greater than B and see what would be the relation between the foci S and S dash and the length of major axis. They are very much related to the point on the ellipse, which we're going to see in today's session. So coming to this, the standard equation of ellipse being x square by A square plus y square by B square equal to 1. So this being the standard equation of ellipse, x square by A square plus y square by B square equal to 1 with A greater than B. Now here, let's see the relation between the foci and the major axis. So for example, I have the focus S and the other focus S dash, and P be any point on the ellipse, say P. Now if S and SI are foci and P is any point on the ellipse, then we know that this is the major axis and this is the minor axis. Is how we identify the major and minor axis. Now let me join P with S, that is SP, and the other focus joined here with this. So joining SP and S dash, I get this to be like this. So joining S with P and S with S dash, I get the relation SP plus S dash P is always equal to T2A, that is a constant. Now this is a relation which we need to identify in case of the foci and the point, that you take any point on the ellipse. If S is joined with P and S dash is joined with P, SP plus S dash P will be equal to AA dash. That implies SP plus S dash P is equal to length of major axis. Is how we identify the length of major axis connected with S, S dash and P. SP plus S dash P is equal to 2A, which is this, the length of major axis. Now, let's see the significance of the mathematical relation which we have obtained in the previous session. SP plus S dash P is equal to 2A. Now with this, the significance is that if I take the ellipse with the length of major axis being 2A and the foci being S, S, S dash, which are fixed, then we can draw an ellipse using, we can construct an ellipse using this relation. So the significance of this is to construct an ellipse is what we are going to see in the session. So as can be seen, if I take two fixed points S and S dash nailed on this board, and then I tie a thread out here of length 2A, that is, I take a thread of length AA dash, and with this length of thread AA dash, I just tie it out to the focus. So I get the thread which definitely extends somewhere here. So I take a pencil or a pen and I put the thread fixed out here. So in this case, by holding tight, this gets straightened and this thread gets straightened, and I just draw fixed tight, I draw the line along the thread. So as I take the fixed end of the string, I do not make it loose, and then I draw, I get an ellipse. So an ellipse is obtained when I just take it and cut it. When I draw it with holding the string tight all the corners. So with this string out here, as I move, I get an exact shape of an ellipse out in case of using the relation SP plus S dash P equal to 2A, which helps us in constructing an ellipse in this manner. Constructing an ellipse using the fixed points S and S dash as nails, and taking one of the point P as a pen or a pencil, I hold the string tight and just move it round so that I get an ellipse out here. Constructing an ellipse using the relation SP plus S dash P is equal to the length of major axis 2A. Auxiliary circle. Now, what is an auxiliary circle? Now that we have discussed about circle, now we're going to interestingly create a circle from an ellipse, or describe a circle around the ellipse, which we call as auxiliary circle. So let's see how an auxiliary circle looks for an ellipse. Suppose I take the standard equation of ellipse x-axis and y-axis, then we know that the endpoints of the major axis are A and A dash. Now with these endpoints, I clearly can describe a circle with the diameter AA dash. Suppose using the diameter AA dash, that is using the length of major axis as the diameter, I just draw a circle or describe a circle along the ellipse. Is how I get a circle out here. Is how I get the circle. So with the diameter AA dash, the circle which I have described on this ellipse is called auxiliary circle. So this is the auxiliary circle along the ellipse, which is given by equation x square by a square plus y square by b square equal to 1, a greater than b. So for this ellipse, the circle is the auxiliary circle, and clearly we see that the auxiliary circle has the radius as a, because the coordinates of a are a0 and a dash is minus a0. Now radius is a and the circle has center as origin, therefore equation of auxiliary circle is given by x square plus y square equal to r square, with r being the radius a square. Is how we define the equation of auxiliary circle, with equation x square plus y square equal to radius square, that is a square. So auxiliary circle has center as origin and radius as half the length of major axis. So this has center as origin and radius is half of length of major axis. Is how we describe the auxiliary circle and its features. Auxiliary circle along the ellipse looks like this, with the equation x square plus y square equal to a square. Eccentric angle. So let's see what is an eccentric angle. As we have discussed about the auxiliary circle being for the ellipse with diameter as AA dash. Now this is the auxiliary circle for the ellipse in standard form. Now for here, the center is origin. Let me take a point P on the ellipse. So for this point P on the ellipse, let me drop a perpendicular on to the major axis. And let me extend this so that this cuts the auxiliary circle at some Q. So this line which extended cuts at Q to the auxiliary circle, we have I join C with Q. Then the angle ACQ, which is denoted by theta, is called the eccentric angle. It's very simple that this line, which makes an angle in anti-clockwise direction, is theta, which is called eccentric angle of point P on ellipse. So this is called ACQ, is called eccentric angle of the point P on the ellipse, x squared by a squared plus y squared by b squared equals 1, with a greater than b. Is how we define the eccentric angle of an ellipse, derived from its auxiliary circle. Angle ACQ is the eccentric angle of point P on the ellipse. Clearly we see that the eccentric angle varies accordingly as the point P moves throughout the ellipse in full 360 degrees rotation and comes back here. We have the point Q equally moving throughout this circle and coming back here. So as P moves, the Q also starts moving respectively, and hence the angle also changes. So the possibility is that the angle can move in all this whole rotation and come back till here, is how we see the angle. Therefore, eccentric angle theta lies between 0 and theta, which is range of eccentric angle. So the range of eccentric angle is that theta lies between 0 and 2 pi. Suppose I take the ellipse in the standard form this with origin x and y axis. Now if I take a point P on the ellipse and join this with angle theta, and let theta be the angle made by this point with center of the ellipse along x-axis. Now with this angle theta, we will define the parametric equations of ellipse. As we have discussed for a circle, the parametric equations were x equal to r cos theta and y equal to r sin theta for the circle x squared plus y squared equal to r squared. Similarly, the ellipse given by x squared by a squared plus y squared by b squared equal to 1 with a greater than b has the parametric equation representation, where I take p is equal to a cos theta and y coordinate as b sin theta, which clearly satisfies the whole of the equation of ellipse, where if I substitute x as a cos theta and y as b sin theta, I get this to be a cos theta by a square and b sin theta by b square, which when simplified as the left hand side simplifies to give a square cos square by a square plus b square sin square by b square, which gives cos square plus sin square, which after cancellation is nothing but sin square theta plus cos square theta, which is 1, using the trigonometric identity. But this is nothing but the right hand side. Therefore, x equal to a cos theta and y equal to b sin theta satisfy the equation of ellipse, making the left hand side equal to right hand side, which gives us the indication that these two are called the parametric equations of the ellipse. The parametric equations of ellipse are x equals a cos theta and y equals b sin theta, with 0 less than or equal to theta less than or equal to 2 pi. and theta is the angle made by the point on the ellipse with this in the anti-clockwise direction from the major axis, is how we identify in this case. So for example, I have another point P dash with this angle being alpha, then the parametric coordinates of P dash is not a cos alpha plus b sin alpha, because this is an anti-clockwise direction, and therefore I take in anti-clockwise direction, this angle would be 360 minus alpha. If this is alpha, this would be the whole of 360 minus alpha is 2 pi minus alpha. Therefore I get the coordinates as a cos 2 pi minus alpha and b sine 2 pi minus alpha, which on simplification gives the coordinates P dash connected with this angle. So every point has every angle for the ellipse through the center of the ellipse. Therefore, every coordinate represents, every parametric coordinate represents the parametric equation of the entire ellipse. Therefore, for each theta, x equal to a cos theta and y equal to b sin theta, with theta between 0 and 2 pi, are called the parametric equations of the ellipse in standard form. The next is the parametric point and its notation. So as we have seen that for the ellipse, x square by a square plus y square by b square equal to 1, with a greater than b, has the parametric equations as x equals a cos theta and y equals b sin theta. Then with this parametric equations, we define the parametric point. That is, the x coordinate always can be written in the angle form as p x coordinate, which is a cos theta, and y coordinate, which is b sin theta. So if I have an ellipse where the point P is making an angle theta with the major axis, this being center, and this is a dash, then the parametric point is given by P of theta, which is P of a cos theta b sin theta. So instead of writing all the time the whole of x and y coordinates, this can be written as P of theta. So P of theta is assumed as P of a cos theta comma b sin theta. So the parametric point is P of theta, with theta lying between 0 and 2 pi. And theta is called the parameter for the parametric point P of theta. Is how we understand the parametric point. P of theta is the parametric point and theta is the parameter. So any point on ellipse can be represented by P of theta, the parametric point. Now generally, the equation of ellipse in standard form is denoted by S, which is x square by a square plus y square by b square minus 1 equal to 0. So standard form of equation of ellipse is denoted by S, given by this. And if suppose I want to find S11 for the point Px1 y1 referred with, then my S1 is xx1 by a square plus yy1 by b square equal to 0. And similarly, for the point x1 y1 referred with, I can find S11, which is nothing but x1 square by a square plus y1 square by b square, but this is a constant which is not equal to 0, or maybe. So if I have S2, I can write this as xx2 by a square plus yy2 by b square minus 1 equal to 0. And if it is S22, it is x2 square by a square plus y2 square by b square is how we get the different types of notations. Say for example, I have 2 points px1, y1 and px2, y2. If suppose I have px1, y1 and qx2, y2, which refers to, then I can find S12 to be x1, x2 by a square plus y1, y2 by b square is how we identify the simplification of this, and this as various types of notations which we use for equation of ellipse and its respective properties. Now next comes the position of a point with respect to the ellipse. Now there are 3 cases where a point can lie in the plane where an ellipse exists. So let's see the 3 different cases of position of a point. Case 1, case 2 and case 3. So in case 1, I have an ellipse with P lying outside the ellipse. The point P lies outside the ellipse. Now I have case 2, where P lies inside the ellipse. And the third case is where P lies on the ellipse. So the 3 cases of the position of the point. One is P outside the ellipse, P inside the ellipse, and P is on the ellipse. So with these 3 cases, we identify that for P which is outside the ellipse in case 1, we have the condition S11 which is greater than 0. So this is identified as the condition. So in order to identify the point to be whether outside or on or inside the ellipse, we simply need to find S11. So if S11 is positive or greater than 0, the point must lie outside the ellipse. And for inside, the condition is S11 is less than 0, and for case 3, where P is on this ellipse, we have S11 equal to 0 is the third case. So case 1, S11 greater than 0, case 2 less than 0, and case 3 is 0. So positive implies P is outside, negative implies P is inside, equal to 0 implies P is on the ellipse.